Hey everyone, Michael Unger here with another edition of Ask an Astronomer. As always, here in the unceded territory of the Musqueam, Squamish, and Tsleil-Waututh, it's event night, so we're getting all prepared for a big event tonight. But before then, we've got lots of questions to get to. We even have a big question from last 2 weeks ago episode that we're going to get to in this episode, as well as lots of other fun stuff. And as always, answering those questions will be our astronomer, Marley. Hey, Marley, what's happening?
Nothing. I got here a little while ago. Not much is happening. Excited for the event tonight. That'll be fun.
Yeah, so it's actually Equinox tomorrow. So do you have any special traditions that you do for Equinox?
No. You ask me this every year, and every year I say no.
Well, maybe you should get some traditions. These are things that we can do to mark the changing of the seasons. Personally, I like to open up some baseball cards. I'm actually going to Edmonton to perform in a dance science piece. That's going to be really fun. So if you're out there watching from Edmonton, I can't remember what the show was called though, but you can message me directly if you want to know info in Edmonton. For now, we are going to focus in on Europa, which is one of my favorite worlds in our solar system. Some fun stuff happening in and around that little world around Jupiter that you can see through a telescope. I've seen it outside at our telescope. So if you are out there watching on YouTube land or Facebook and you have a question about any of the things we're going to talk about, as you've seen the last couple episodes, the big question sometimes gets a big focus. So ask your questions into the chat. We will try to answer them before the end of the half hour. Marley, what is up with that beautiful Europa world?
Well, what happened earlier today, about noon-ish, a press release dropped from NASA regarding the James Webb Space Telescope and that it had imaged and also somewhat kind of discovered something that was happening with Europa, which is very exciting.
Something's happening with Europa. That is like the best news that I could possibly hear today.
Yes, well, they've detected something pretty interesting. Just a background on Europa. This is an image from NASA, or two images rather. The one on the left is the approximate natural color appearance of the moon. So this is what our eyes are, as close to how our eyes would see it if we could get up close to the moon. And on the right is a false color image that combines violet, green, and infrared light, kind of showing different parts of the moon. So dark brown areas are rocky material that have been derived from the interior or brought on by impact, or a combination of the two. Europa is about the size of our moon, which is always fun to think about. Earth has a really big moon as far as moons go comparative to their planets. So it's interesting, but it's about the size of our moon. This image was taken in September of 1996. So this isn't the Webb image. This is to just give a background on the moon itself. Europa is thought to have an iron core, a rocky mantle, and an ocean of salty water. And it's really maybe one of the best worlds to search for life, after Mars. Like, aside from Mars, Europa would be the next best bet. Scientists are almost entirely certain that beneath the surface is a saltwater ocean with about twice as much water as on Earth. And stemming from all this talk of the ocean and the detection of the ocean, there comes the Europa Clipper mission that's planned to launch in 2024 that will investigate whether it can support life or not, right? So this underwater ocean, how is the water melting underneath all of this ice? There has to be some sort of heat source. It starts to fit in with maybe we have some interesting creatures similar to the creatures we have on Earth that surround hydrothermal vents, right? So this very interesting extreme environment, but one that we see mimicked on our own world in certain places. And this was all prior to the Webb detection.
The key word there that you said, interesting creatures. I mean, because once we start to venture into this territory, it gets people like me very excited about the possibility of interesting life in our solar system.
Yeah, I mean, would it look like us? Probably, most likely not. Like, we're not built to survive underwater, no matter how hard we try. We're not. It's just not how we evolved to live. But creatures that are not us have evolved to live in these very interesting environments, high salinity environments, very cold environments, and environments that mimic, around a hydrothermal vent. Those are some of very odd looking creatures, but they've evolved to survive there. So maybe who's to say they haven't evolved to survive around here? Haven't detected any of them yet, and that's not what Webb detected.
Yeah, like the Gungans, right? Like Jar Jar and the Gungans, they adapted underneath the ocean.
Yes, they're very odd, though. I don't fully understand how the Gungans work evolution, but I suppose it's not the point for me to understand either. But sure, like the Gungans. The JWST detection is what's being shown. So these are the images that came out earlier today. In fact, 2 papers were published today regarding the JWST detection. I have not had a chance to read them yet because they were published and then I got to work and I had to do other stuff. But the brief notes is what you're seeing is a map of Europa's surface. The first image is NIRCam. It's an infrared image, which is why it's appearing as this blue and white as opposed to that natural color image I showed you before. And then the next 3 are compositional maps or compositional images derived from NIRSpec, which is the near infrared spectrometer, which is used to detect different elemental compositions. And in the following 3 panels, not the one where Europa's blue, but in the very pixelated ones, the white pixels correspond to carbon dioxide. So that's the big detection, is that they've detected carbon dioxide on the surface of Europa in this very specific region called the Terra Regio, which is what they call, quote, disrupted chaos terrain, which is probably one of the coolest string of words I've ever heard in my life.
Yeah, and also a good metal band name too.
Would be a very good metal band name with like looks like a shrub, right? And the text looks like a tiny little shrub. But that's what they've detected in this part, kind of this big to the center right. So there's kind of 2 places you see these pixels, but the Terra Regio is this to the center right of the 3 images. In the second and third images in particular, or the second and third panels, so these 2 here, show evidence of crystalline carbon dioxide, so not carbon dioxide in its gaseous form, but like in a crystalline form. Mm-hmm. And the 4th panel is indicating complex forms of carbon dioxide. And so with these observations, the team that observed think that they have evidence, at least observational evidence, of that the carbon dioxide or the carbon on the surface comes from the ocean. This makes sense. There's a couple things going on with it. Terra Regio, the region where they're seeing this high amounts of concentration, is what we call geologically young. So Earth, for example, is geologically young. The rocks are being reformed. There's, wearing away, erosion. There's changes happening to the surface. The moon, for example, is somewhat geologically young. Lots of impacts move the surface around, but other planets are just very old, right? The moon would have a geologically, some regions, older surface than Earth, for example, because there's no weathering events, there's no water washing away. The things that happen to the moon are impacts, and that will change the geological age when that impact happens. And so this Terra Regio region is generally resurfaced terrain called chaos terrain, which again is very fun. Mm-hmm. What that means is the surface ice on Europa has been disrupted, and there's likely been an exchange of material between that subsurface ocean and the icy surface above. CO2 is not stable on the surface of Europa, and so it's very likely that this concentration is very recent, right? It wouldn't last for a very long time. It would be a geologically recent event on, geological timescales, which are still, millions of years, but nonetheless, it would be fairly recent, which, makes sense because it's found and concentrated in this region of very young terrain. So all signs are kind of pointing towards this just appeared, and it's probably due to an interaction between the subsurface water and the icy surface. The 2 papers published today, I haven't had a chance to read, but they go into more depth about this imaging and how it was taken. I'm not sure if they're open access or not, but they would be available through the JWST website. They often link towards them, and it will probably be one of the first things that comes up in the appropriate journals if you were to look for it.
Right. So I guess I'm curious, like in these papers, are these astrobiologists that are doing these studies and presenting these papers?
It's like a combination of people, I would assume. I'm trying to remember the exact name of who was the lead of the team. I think his name was Guillermo was his name, but is kind of like the lead. He's cited in all of the writings. I'm not sure if he's an astrobiologist specifically, but they would be more of the planetary side of astrophysics than the stellar astrophysics side.
Yeah, it's interesting because this gets been now very specific. Like this type of work, I don't think it ever really been done before because we never really had the types of observations to get this kind of very precise data. It's very exciting to create these new fields. I mean, of course, astrobiology is not that new, but it is getting more and more very important in the study of looking for life.
It is. And I mean, there's been studies in this specific region before. Very earlier on, this is a Galileo image, which is why it's so grainy. But earlier on, this is the Terra Regio, the region where they've detected this carbon dioxide. Earlier on, there was a detection of sodium chloride or table salt, right?
Mhm.
So a team of scientists detected sodium chloride in the same region, which is a principal component of sea salt. So this area has been looked at before, but this is kind of the biggest, carbon dioxide detection that they've done.
Very cool.
Which would be done with JWST, because it's carbon dioxide would sit in the infrared, right? So we needed to get a telescope that could see it, really.
Yeah, really interesting. This brings up a question. I think we got this on an Ask an Astronomer once, which was when we were talking about JWST and what would happen. I don't think it was possible, but what would happen, if we look back on our home planet and I guess do the same sort of exercise that we are doing with a lot of these worlds, looking at the exoplanets and Europa and looking for signs of life. And what we would see if we were looking at our home planet, would it be apparent just by looking at observations? And is that what we're looking for? When we're looking at a world like Europa, of course, we want to know what's inside of the ocean. But this type of discovery on the surface of the ice seems very surprising. And is that an indication of life? Would we see that same type of CO2 coming from our oceans if we were to look at our planet from afar with an infrared telescope?
So it's not exactly the same, but it's still exciting because of the fact that there's carbon, right? So we can only understand and search for life using how our planet works as the backdrop, right? Because we understand mostly how life on our own planet works. And so that guides our steps when we start to look at other worlds. So in the case of Europa, there's an ocean, which means there's water, which is necessary for life as we understand it. Now with the detection of carbon dioxide, there's carbon. Somewhere there's carbon in and amongst the planet, in its oceans or in the surface, who knows, but it's there, which is also important. If you've heard the phrase carbon-based life form, right? It's kind of the building block or one of the building blocks of how we get life on our world. And it's crucial to life on our world and life as we understand it. Additionally, Europa has a very thin oxygen atmosphere. It's mostly composed of oxygen. So there's also oxygen, right? So we have carbon, water, and oxygen, the three things that really we look for when we're looking at other worlds. It doesn't indicate that there's life. It's not in the concentrations to indicate that there's life. That wasn't the purpose of the detection to say it came from life, but it definitely pushes things in the right direction and certainly sets up the Europa Clipper mission with new targets to study.
Very, very cool. All right. If you are wanting to know more about Europa, the big discovery, the big news of the day, if you get excited about hearing something's happening up with Europa, then put it into the chat. We will answer your questions for the next 15 minutes, but we're going to dedicate the rest of the show to a question that we got last episode. And again, it was one of those doozy questions that you can answer on the surface, but actually is really fun to get into and get into the complexity of how we study stars. We look up at the sky with our eyes, we can see tints of color. And, I'm always amazed that when you look up the stats on these stars, we have so much information from these stars that are so far away. And the question was related to how we can determine, was it the age of the stars and the color of the stars and how they all interconnect and how we know all of that?
Yes, that was the main question. Before we jump in, I want to clarify. I mixed up the PI's name for the Europa detection. His name is Dr. Geronimo Villanueva. He's a planetary scientist at NASA Goddard, and he kind of specializes in astrobiology type stuff is kind of his focus. So I combined his first and last name and made the wrong name. But Dr. Geronimo Villanueva is his name. So congrats to him and his team. But yes, stars. The last question had to do, I cannot remember the question. I also cannot remember exactly who asked it, but it did make me dovetail into how we know the mass of stars, how do we know how bright they are, and how do we know what color they are? How do all those three things intertwine? So as we know, stars can come in different shades, different colors. We have blue, a bit of yellow, and then we can range into red as well. And what causes those colors has to do with what the star is made up of, and also has to do with its temperature. And that will also kind of filter down to its mass and kind of what's going on with the star at its time in life. So we have a specific way of categorizing stars or assigning a spectral class to them. And it's thanks to Annie Jump Cannon, is the woman who came up with the system that is still used today. She was hired in 1896 by Harvard Observatory as one of their computers. She examined data collected by the Harvard Observatory and manually classified over 350,000 stars, which is a lot to do by hand, as you can see in her picture there. And she came up with the stellar classification system. So this is the OBAFGKM. So you may have heard our sun is a G-type star, right? She is responsible for coming up with this classification system.
Oh, be a fine gremlin, kick me.
Sure. Yeah, there's different ways of remembering it. That's not one I've heard before, but it works. One way to categorize stars is based on their spectral class, or the star's color as it's related to the surface temperature of the star. For whatever reason, this is called the Harvard system of spectral classification, not the Cannon system of spectral classification, which I disagree with. It should be named for her. She came up with it. AJC, Annie Jump Cannon, she looked at the strength of absorption lines of hydrogen. So going back a few episodes, I think we talked about spectroscopy and those hydrogen lines. How strong those absorption lines of hydrogen are, she assigned a classification based on that way. So OBAFGKM was already the classification scheme. It was actually developed by Wilhelmina Fleming and Antonia Maury, who were also working with Harvard around the time. Annie Jump Cannon built on it and made it better. Mm-hmm. And she realized that she was classifying stars according to their temperature, and her method of classification was eventually universally adopted by the astronomical community. It's been slightly modified since then with different subclasses that denote temperature and luminosity because they're tied to each other. How hot a star is will also tell you how bright it is, and it'll also be a specific color.
And if I recall correctly, because I remember we did talk about this last time, the reason that it's not like in order of the alphabet was because like the A and B stars were like the first ones that were classified, right? And then like in the end, when they figured this all out, it kind of got all jumbled up.
It gets all jumbled. Yeah. So they were already using OBAF, GKM, and then the order got switched around because then they started. Well, Annie Jump Cannon started classifying based on the strength of the hydrogen lines as opposed to the different method that was being used by Wilhelmina Fleming and Antonia Maury. It gets built upon and redone, but the way Annie Jump Cannon did it is the way we still use it today.
Right. Very cool.
She published her method in 1924, but her work started in the late 1890s and the early 1900s. So she was working on this for a very long time before it became published and adopted. This leads into around the same time, two other astronomers were trying to figure out how to categorize stars. This was a very big puzzle at the time. Like, how do we categorize them? It had to do with, well, humans like order and humans like to put things in boxes, but also trying to find distances to things and learning about stars themselves. So in 1911 and 1913, two other astronomers were trying to figure out how to categorize stars. Ejnar Hertzsprung plotted absolute magnitude of stars against the brightness. So absolute magnitude is a measure of how bright the star appears to be to us. Now we know that this is essentially plotting the temperature. And Henry Norris Russell plotted spectral class and absolute magnitude, the different plot that I didn't show. And then we came on and combined them, right? So this is why this graph has four different axes on it. We have the absolute magnitude, the spectral class. This was Annie Jump Cannon's, OBA, FGKM, luminosity compared to the sun, and the effective temperature, because they all tie in with each other. So when astronomers are measuring, say, the age of a globular cluster, they will plot the stars according to the absolute magnitude, spectral class, or luminosity compared to a temperature. They'll plot them, and you'll eventually get a plot that looks something like this. And where the main sequence ends, or where the cutoff point is, can actually tell you the age of the cluster. So there's lots of different spin-off uses of a diagram like this, known as the Hertzsprung-Russell diagram. And it shows the relationship between the temperature and the luminosity of a star. It's not random. And it's not like astronomers went into it trying to find a pattern. It was more of we've plotted the same thing so many times and the graphs look the same. So these all must be related.
Yeah.
We end up plotting them into groups. So most stars are on the main sequence. Our sun is on the main sequence. 90% of stars are on the main sequence. Sirius is on the main sequence, Vega, Altair, they're all main sequence stars. But main sequence stars can be different colors and different temperatures and different sizes. And that has to do with how like the star's initial formation, right? How large the protostar was when it began fusing hydrogen into helium. But all the main sequence means is that you're fusing hydrogen into helium. That's the current stage of life a star is in.
Right. Yeah. There's a whole bunch, as the star gets bigger, then it's fusing those heavier elements, right?
Mm-hmm. And so it'll move off the main sequence. Once it stops fusing hydrogen to helium, it moves off the main sequence. Depending on where it is, we'll kind of tell you where it'll end up. And it'll have an associated temperature change, a spectral change, a luminosity change, even as it moves around on the main sequence. So the sun, for example, will, go through all of its fuse everything. It'll move off the main sequence. It'll become a red giant. So kind of in this area here. And then it will fuse, run out of stuff, and it will drop down into this corner, the white dwarf section of the HR diagram, right? So you can kind of chart a star's life through this main sequence. Assuming you've got everything about the star right, you can chart its life through the Hertzsprung-Russell diagram.
Yeah. And then once you get into, looking at that, then you get into some like very complicated things with what's happening inside of the star and that cycle of fusion that's happening, right?
Yeah, so it starts to go on. So this is kind of explaining what's going on inside of a main sequence star, right? Like our sun. So main sequence stars characterized by their source of their energy, which is the fusion of hydrogen into helium inside of the core. The main form of this is the proton-proton chain, which is the main form of what's happening in our sun. So there's actually a few different ways to get from hydrogen to helium. Our sun mainly does this one form of it, one form of fusion. 4 hydrogen nuclei or protons combine to form a helium nucleus by the end. There are a lot of steps in between, as you can kind of see on the diagram here. And then 2 hydrogens, it kind of goes through the steps. I don't think I want to read through all of them because it's quite long. There's a lot going on that I was tested on that I don't really remember much of anymore.
I mean, we are getting into like almost university level astrophysics here.
I'd say this is early university, high school, maybe.
Yeah,
I think I learned about this in high school. I think, yeah, it looks familiar to me anyway. Can't peg when I first learned it, but how fast they go through the hydrogen and how much they go through the hydrogen and how much is available depends on the mass of the star. And that's determined when the star is first born. The star's first being born is still something we're studying and trying to get, all our ducks in a row on. JWST is helping with that. It's actually able to see these very young stellar systems. And when I say young, they're young relative to the lives of stars. They're still a few million years old, but that's still pretty young in a star's life. And when it's first moving on the main sequence and when it's first forming, it becomes a fun thing to study and to help us figure out the tie between the mass and the ultimate end of the star, right? We have a good blueprint and a good idea, but it'll be nice to confirm it, to the best of our ability using this telescope. Mm-hmm. This is the CNO cycle, which I kind of threw in to show what happens in these higher mass stars. So our sun, is average, I guess. Higher mass stars are about 1.5 times the mass of our sun or more. And this type of energy production dominates, it stands for carbon, nitrogen, and oxygen. And so it requires a proton or a hydrogen nucleus to fuse with a carbon, a C12 nuclei to start the cycle off, right? So it's still dependent on hydrogen. But it goes on to make carbon, nitrogen, and oxygen. And then eventually you get a helium nucleus at the very end. At one of the steps, you get a helium nucleus. This dominates in higher mass stars because of temperature. You need a much higher temperature to kickstart all of these nuclei into fusing with each other. Higher mass stars have a stronger gravitational pull in towards the core, which leads to higher core temperatures, which means you can have reactions like this happening. Larger stars, more gravity, increase core temp, increase the amount of pressure coming out, which means larger things fusing. But this still counts as a main sequence star. It's still fusing hydrogen into helium. It's just going about it using carbon, nitrogen, and oxygen, as opposed to the proton-proton chain. Still 2 things happening. And all of this will affect luminosity, brightness, and can be determined from luminosity or brightness and color and all that sorts of stuff.
I'm imagining now, like the person that asked that question, I'm hoping that they, they stuck around and they'll watch this afterwards on YouTube, that this is like a question on their test or something. And we've like sufficiently helped them answer their question. It is a bit complicated, but it does set us up for what we're doing here tonight, because we have a very cool event with Catherine Crowther from UBC talking about basically the next step of once a star essentially dies or it comes to the end of its life after it stops that fusion process, right?
Yes. Yeah, Catherine will be talking about the ends of massive stars. So not stars like our sun. They're not what we're focusing on tonight. It'll be the result of ends of massive stars. So stars like Betelgeuse and about that size, and what happens to them, their stage after they've died.
Awesome. Well, if you're out there watching, and there's still tickets left for our event tonight. It's our 19 plus event. So unfortunately, anyone under 19, you'll have to come back, but you can always ask your questions here. We're going to be talking about neutron stars. We're going to talk about pulsars. We've kind of dubbed them as undead stars, which I find kind of fun. So we've got some Walking Dead comics that we're going to be giving away as prizes for tonight, even though it's a month away before Halloween, but it's always fun to delve into weird zombie-ish things at any time, right?
I feel like as soon as it's officially fall, it's fine. It's like it's now Halloween season. So.
That's right. There you go. So officially, like at the end of the day tomorrow, I think like the actual time of equinox is actually close to midnight.
It's like 11:50, p.m.
Yeah. So like today is the actual full last day of summer. It is actually still feeling like summer out there. Still sweating in our offices today. Before we end the show, we actually did get one question in, which maybe that'll help set us up, although we do have a special guest in 2 weeks. But the question was kind of going back to, I think, maybe even the previous episode, talking about the last big news that JBST came up with, which was exoplanets.
Oh, yeah.
What are the most interesting exoplanets that you've heard about, and why?
Oh, I like the TRAPPIST system because I like studied it for half a second in university before I was like, galaxies interest me more. But I really like the TRAPPIST system. The most recent news that's come out of JWST about the TRAPPIST system is that probably bad, no life on those ones, despite the fact that it was so exciting. They were all Earth size. They were rocky, they were in the habitable zone. 2 of them are tidally locked with the star. So one side is always facing the star. One side is always facing away, much like our moon, tidally locked with Earth. And the temperatures on there are consistent with no atmosphere whatsoever, or at least a very thin carbon dioxide atmosphere, like in the 500s of Kelvin. Not great for life, not a place for life we'd expect to find, at least not life like us. So, but frankly, anyone who really studied the TRAPPIST system could have told you that. I think they were pretty certain those things were tidally locked with that star. They're very close, and not a great bet. But those are kind of my favorite exoplanets I've heard of. There's a couple other ones that I know of. Like I never remember their names though, because the names are just barcodes. They're just strings of letters and numbers. But the one, I think it's a WASP one, WASP 96b, maybe I want to say, is the one that's being ripped apart by its star because it's tidally locked to the star. It's a gas planet that's being ripped apart. But those are kind of, I don't know, the ones that are desolate and unhappy kind of are the coolest ones. There are actually exoplanets that orbit pulsars, which is very cool. Those are interesting to look at too.
Now, what does that have to say about you and your sensibilities, that you like the cold and desolate exoplanets?
I'm just a cold and desolate person who's knows. Yeah, knows. No warmth here. No, I just like them. I like that they're so extreme. It's interesting. Earth is extreme in its own right, but those ones they're just so different, I think, is what makes them interesting. So completely different from our own experiences here in our solar system.
Exactly. Yeah. There's any planet that is potential, to house some water, or potentially be that world. I can't remember the world in Ahsoka right now. I'm watching Ahsoka, no spoilers, but there's some really cool scenery. These red leaves, it just was perfect for fall. If anyone's been watching Ahsoka, I can't remember the name of that world though, but it looks so cool because the leaves were just so red and it was perfect for camouflage. Sorry, I may be giving away too much away about Ahsoka. Another question from Keith about what the name of that. I had to look up the name of the show, which is actually sold out. I just went to Eventbrite. Connections and Collisions, a new cabaret, which is where I'm going to be performing. I'm going to be the narrator for the science bit as dancers are dancing, showing how atoms work inside of our bodies.
You mean you're not dancing?
No, I'm not dancing. I know you would like to see that, but it ain't happening.
That would be fun, like a giraffe on roller skates.
Well, I mean, speaking of that, we are going to be doing our listening room, and the one in October, that would be the type of music that I would dance to. The playlist, which is all going to be about Goth Universe. Goth Universe is going to be our listening room on October the 28th.
Stay tuned to learn how Michael dances to goth music. I don't know how that works, but.
And that's it for this episode of Ask an Astronomer. Thank you all for joining, and thank you all for your questions. In 2 weeks, we do have special guests. Like I said, we are going to be having some students from a high school that are working on an eclipse project. We do actually have a partial eclipse that is going to be visible here in the Lower Mainland on October the 14th, but this is all leading up to the total solar eclipse that is going to be visible on the eastern seaboard. We're not going to see it here on the West Coast, but these students are going and they're doing a really cool project that they're going to tell you about in the next episode of Ask an Astronomer, which is going to be on October the 5th, 4 p.m. Pacific time. Thank you all so much. Take care.